In this short lecture, I'm going to talk about geography's tools, not only because geography's tools are important in a disciplinary sense, but because we're going to be using a lot of these over the course of the semester. Geography's tools are important because, as I talked about in the discussion of what is geography, geography sees itself as a spatial science. And by spatial science, what that means is that the data that we use as geographers is geographic in nature. There is a way to place those data onto the world geographically. We refer to that as geospatial data. It means we can map it. It means we can take pictures of it from a satellite or an airplane. It means that we can analyze it in a geographic way. All of these different things are ways that geographers look at the world. But they all ultimately begin with the ability to actually put a piece of data someplace on the planet and understand why it's there. So that brings us to the idea of latitude and longitude and the creation of a coordinate system on the planet. The Earth is a sphere. Mostly it's a sphere. It gets a little more complicated than that, but we don't need to get into that. And as a sphere, it needs to have a special way to find coordinates on it that are X and Y coordinates because it's not two-dimensional. We do this in geography through lines of latitude and lines of longitude. There are actually other coordinate systems out there, but we're staying with the basics in Geography 111. Lines of latitude are sometimes referred to as parallels, and the major parallel is the equator. Lines of longitude are sometimes referred to as meridians. They go from the North Pole to the South Pole, and they cut through the planet, starting at what's called the prime meridian, which goes right through London, actually, of all places. The North Pole and the South Pole are, of course, an important part of this whole process in understanding how it all works. And this is something you'll have to go to the text and look at a little bit more. But there are all sorts of interesting diagrams there that will show you how lines of latitude are created, number one, essentially by making a right angle between the North Pole, the center of the planet, and then out to the equator, which is equidistant north and south from the North Pole and the South Pole, which you can see right here. An angle is then drawn between 0 at the equator and 90 at the North Pole. And that's how we create the first coordinate, which is north or south of the equator. Then we have to find things east or west of the prime meridian, which is in Greenwich, England. And we do that by essentially looking at the Earth from above like a circle, which has 360 degrees. Here are a couple other diagrams that I quickly made that attempt to show this. First, you have a hemisphere where you essentially slice the planet in half. And once you have that hemisphere, you can find places north or south of the equator using that angle that I talked about before. To create lines of longitude, you look at all of this either from above the North Pole or below the South Pole. And of course, there's really no above or below. It's just convention to think of north at the top. And then we divide the planet into 180 degrees, either east or west of that prime meridian. So an example of all this would be someplace being 40 degrees north and 77 degrees west. 40 degrees north of the equator, 77 degrees west of Greenwich, England. That's further subdivided into minutes, and then minutes are divided into seconds. There's 60 minutes in every degree, and there's 60 seconds in every minute. So you can get to very precise locations, like we see right here. That number can also be expressed as a decimal point, 40.66906, minus, because it's west as opposed to east, 77.793551. You can actually plug that into Google Earth if you want to, and you will actually go see the family homestead in central Pennsylvania, where I am originally from. We collect geospatial data on the Earth, and one of the ways we do that in the modern era that makes it quite precise is through GPS, Global Positioning System, which actually includes the American system called GPS, but then there are a bunch of other countries' systems that we use as well, including the Russian and the European, and to some extent the Chinese system as well. And these GPS receivers that we might have on our phone or that we might have on a smartwatch or some other receiver essentially collects some special signals that are coming from satellites that are positioned all around the planet. And then that receiver essentially goes through a mathematical process to determine where we are on the ground based on when it has received these particular signals. So when your GPS works on your phone or watch or whatever, you're actually receiving data. You're not sending any data out whatsoever. Then you're triangulating your location based on when that data comes in. And it allows us then to see where we are in Google Maps with a little blue dot. That might then help us find our way someplace like Denali National Park. Or if we have it on our smartwatch and we go for a run or a hike, or in this case, an orienteering event someplace, we're able to later download those data and see where we went. This picture on the right shows me using a fancy GPS, a GNSS, which collects data not just from GPS, but also from the Russian and the European system to find a very precise location, usually within an accuracy of under 1 meter. Once we have those data, however we've collected them, we can map them. And we're going to be using maps throughout the course of the semester. In fact, the first assignment, you have to look at maps a little bit. So I just want to talk about some general things related to maps that, again, you can look at in the textbook and get more information about it. The first is that maps, of course, are a scaled model of the world. So some maps show more detail, some show less, and there's usually some sort of bar that shows that to you on a map. But maps sometimes have a little fraction on it as well. And those fractions tell us what some unit is on the map compared to what it is in the real world, whether it's an inch, a centimeter, a thumb length, whatever. We'll talk about those scales later. But when you're looking at your maps for the physical geography assignment, I want you to note what that scale is. The Earth's surface is on a sphere, but maps are two-dimensional. We flatten things out. And we do that using what are called map projections. And map projections aren't going to play a really big role in this course, but I think it's worthwhile knowing that any map that you look at has been projected into a flat surface and is distorted because of that. Different types of projections distort things in different ways. And I'm going to show you some examples of that in just a second. I'm also going to show you some examples of all the different symbols that can be used to model the real world on a map so we can make some sense of interesting geospatial data that we might have collected. And this will be both through different types of thematic maps that use shading and shapes and lines and dots to show things, or topographic maps that use little brown lines that you'll be using in this class to help us understand physical features. So first, here is North America projected using 3 very different projections. This is called an Albers projection. This is a Mercator projection. And this, I believe, is a Peters projection. And you can see that North America looks different depending on what projection you're using. It gets bulgy, or it gets some areas get too big, like Alaska, or it gets all weirdly stretched out. You should always be thinking that maps have projections and that they distort the world in different ways, and we should be cognizant of that. Here's a bunch of different maps that I've made, just showing all the different ways that things can be symbolized on a map. We can use different colors. We can use different shapes and sizes, like these graduated circles right here. We can use lines with arrows to show things. Or we can just use little tiny special symbols like these coffee shops and coffee stop symbols that I've used to show where all the coffee shops and stops in the Anchorage Bowl are. We can use special different types of symbols like this, what's called a waffle chart right here, that essentially uses little blue or red bubbles to show whether a house is represented by a Democrat, a House seat is represented by a Democrat or Republican for each of the states. Or we can use all sorts of different types of pictographic symbols like this map right here that uses colored lines as well as a different way to show topography on a map. Maps do all sorts of really beautiful, wonderful things, and they're pretty cool. And of course, I'm a geographer, and I've made my life looking at maps. One of the types of maps that we'll be looking at a lot in this class will be topographic maps. These are maps that use special brown lines called contour lines to show elevation. And that's something I want you to explore a little bit more in the physical geography assignment. In addition to using elevation symbols, maps also use colors to show vegetation, swampy areas, streams, glaciers, all sorts of other things. And you'll be exploring that a little bit. In addition to mapping data, geographers also use data that are remotely sensed. Remotely sensed data are data that have been collected either by a satellite or by a plane or by a drone these days. Sometimes the data that's collected is light, in other words, a photograph. But other parts of the spectrum are also collected as well. And increasingly, geographers and cartographers are using laser-based data, or what's called LIDAR, to create very fine images of the surface of the Earth, as well as study things like vegetation and buildings. Here are some examples of remotely sensed data. These are very accurate photographs that are geo-referenced, so we can use it as geospatial data of the Anchorage area. This is someplace in Midtown. The municipality has a whole set of these very accurate images. This is a part of Denali National Park, one of the backcountry sectors. And what we're seeing right here are different wavelengths of light that are reflected from the surface of the Earth and then are composed into a composite image using different colors to show different densities of vegetation, essentially. And then over here we have an example of LIDAR data that was collected by the municipality of Anchorage that allows us to see very fine features in Bird Valley on the way to Girdwood. You can see some cool glacial features in here that we'll probably talk about later on in this course. All of these data are geospatial data. All of them help us to understand the world. And one of the ways that we can sort of pull them all together is through what are called geographic information systems. These are systems that allow us to use all sorts of different types of geospatial data, manage those data, layer them, allow us to visualize them and analyze them. And they are increasingly important and being used all over the place, both in desktop applications and also web-based information systems as well. Google Earth, which you'll be using in this class, is an example of a GIS, though it's very lightweight GIS compared to the things that professional geographers use. There are so many different types of online interfaces. I've created just one slide here showing some of the GIS systems that I interact with online on a regular basis. The U.S. Geological Survey does a recent earthquake GIS data page that you can go to, that you can see where the most recent earthquakes are. Here's a map from, I believe, the Department of Agriculture that collects data on snow depths around Alaska that I often look at when I'm trying to figure out where I might go skiing or might go snow camping. In the same building where I'm located is the Alaska Center for Conservation Science. They have all sorts of GIS resources that they create. This is one that shows invasive species around Alaska with different colors of red showing where there's a greater concentration of invasive species. And then finally, a GIS that many of you might use is the Nordic Pulse, which is a GIS system used by the Nordic Skiing Association of Anchorage that essentially lets us see where trails have been groomed, how recently, and what condition things are in. That's a GIS system, and it's been created with geospatial data. Even though it's something for public consumption, it's still very much GIS data. So these are all things to explore a little bit and learn more about, and very cool stuff. And I'm always happy to geek out and talk with people about maps and mapping and GIS and collecting your GPS data on your watch and things like that.